Energy, the environment, the economy, and you. What is energy? Energy is the ability to do work or cause change. It exists in different forms and can be transferred or converted, but cannot be created or destroyed in accordance with the law of conservation of energy. It is essential for everything from natural processes to human activities like electricity generation, transportation, and heating. Examples of energy types are kinetic energy, which is the energy of motion like that of a moving car, wind, flowing water, or a rolling ball. Potential energy is stored energy dependent on position such as a stretched rubber band, water behind a dam, or a book on a shelf. Thermal or heat energy is the consequence of the movement of atoms, molecules or ions in solids, liquids and gases, and can be transferred from one object to another. The transfer or flow, due to the difference in temperature between the two objects, is called heat. Examples are sunlight, fire, hot coffee, or a stovetop burner. Chemical energy is energy stored in chemical bonds, for example, food, gasoline, batteries, or coal. Electrical energy is the flow of electric charges like lightning, power from outlets, or a battery powering a flashlight. Nuclear energy is derived from atomic nuclei like the fusion in the sun or fission in nuclear power plants. Radiant energy is derived from electromagnetic waves including light, X-rays, radio waves, and microwaves. Sound energy is produced by vibrations like music, a ringing phone, or someone speaking. Global warming is an excess of thermal energy that is being primarily stored in the world's oceans. Hero or Heron of Alexandria, in the 1st century AD, demonstrated the conversion of heat to work with his working steam engine he called an aeolipile. This wind ball was able to lift a weight, thereby producing work. Between 1844 and 1850, the English scientist James Prescott Joule worked on the problem of the relationship between the amount of work spent to bring about the liberation of heat and the amount of heat liberated by that work. He used a paddle wheel device submerged in a heat-insulated vessel attached by a series of pulleys to a weight. As the weight fell, it imparted rotation to the paddle that in turn produced heat inside the vessel. The work done was determined to be equal to the decrease in the potential energy of the weight as expressed by gravity times the distance the weight fell. As a result of multiple experiments, Joule discovered the proportional relationship between spent work and the quantity of heat obtained by his device was equal to a 1 kilogram weight falling 427 meters, warming 1 cubic meter of water 1 degree Celsius, which became a joule, which is also equivalent to 4.19 watts. By reversing Joule's experiment, an ocean thermal dam embodied by the ocean thermal energy conversion method can, with the assistance of a heat engine, convert a tropical surface heat of 30 degrees and a deep water cold sink at 4 degrees Celsius at a depth of 1,000 meters into a theoretical potential energy of a 1 kilogram weight at an elevation of 11,102 meters. The Carnot efficiency of such an arrangement using the thermodynamic geoengineering method is 7.6%, and the system has to be reversible, so the actual potential of the weight is 421 meters, which is just under twice the height of the Hoover Dam. And this potential exists universally in the tropics. The importance of energy. In 1922, Alfred Lotka, a U.S. mathematician, physical chemist, and statistician, famous for his work in population dynamics and energetics, building on principles from statistical physics and the second law of thermodynamics, particularly the work of Ludwig Boltzmann, articulated the maximum power principle that living organisms need available energy from their environment to survive and thrive, and that organisms that best harvest energy from their environment will be more successful, leading to larger populations and greater biomass. In his 1950 doctorate dissertation, H.T. Odum, an American ecologist best known for his pioneering work on ecosystem ecology, proposed, based on Lotka's work and Charles Darwin's theory of natural selection, a fourth law of thermodynamics that proposes maximization of power for valuable purposes is the criterion for natural selection. In his 1996 book, Environmental Accounting, Emergy and Environmental Decision-Making, Odum proposed a fifth law suggesting energy flows through the universe are organized in a self-organizing hierarchy for maximum empowerment. And in 2001, Odum proposed the coupling of biogeochemical cycles to energy transformation hierarchies in a sixth law that proposes energy, must be degraded to concentrate materials, and that the quantity of material flow also decreases in each successive step in a series of energy transformations. In a paper, A Seventh Law of Thermodynamics and Its Climate Implications, this writer proposes a seventh law of thermodynamics that is an amalgam of the maximum power principle that states, during self-organization, system designs develop and prevail that maximize power intake, energy transformation, and those uses that reinforce production and efficiency, and the law of supply and demand, which states that if a product, including energy, that is a product of an exothermic reaction thereby releasing heat into the environment, is in high demand and low supply, the price will increase. Conversely, if there is low demand, as is the case of an endothermic reaction that imports energy from its surrounding environment, the energy is a reactant and is in plentiful supply, the price of the energy will decrease. Energy is vital to all living organisms, but the economic imperative drives most of humanity. Therefore, the lower the cost of energy, the more our society can consume, and the more successful it will be and more capable to address its other concerns, including the environment. The most plentiful and cheapest available energy source is impeded by its perceived high capital cost, but the seventh law of thermodynamics can break this embargo and complete the suite of thermodynamic laws, making them a unifying law of energy and economics plus a blueprint for a holistic solution to one of the century's most significant challenges. Energy sources. Reasonably recoverable reserves are the quantity of a resource reliably determined to exist, and that can be recovered under current technological and economic conditions. To be reasonably assured, there must be a high level of confidence in the existence and recoverability of the resource based on geological evidence and engineering data, which is often obtained through drilling and sampling of an area. Furthermore, to be recoverable, there must be enough of the resource it can be extracted with existing technology and under current economic conditions in view of the cost of extraction, market prices, and regulatory or environmental constraints. Perez and Perez, in a paper Update 2022. A fundamental look at supply-side energy reserves. For the Planet for Renewable Resources, extended the definition of reasonably recoverable reserves to a 30-year life cycles to be consistent with the long-term reserve numbers for conventional finite resources, which is the 30 years commonly used for economic assessments and planning purposes for renewables energy undertakings. All reserves in the following graphic are reported in terawatts per year and given the 30-year time frame considered for renewables and consumption, as terawatts per year to the 30th subscript. The figure depicts finite and renewable planetary energy reserves and their 30-year potential, with the volume of each sphere representing energy potential. Perez and Perez noted for ocean thermal energy conversion, a recent review by Langer et al., states the technology's global potential is of the order of 30 terawatts per year. However, the authors caution that OTEC's economic potential is unknown as it is still an immature technology with no commercial plant operating. Therefore, they use the conservative estimate of 3 terawatts per year. As is demonstrated in the paper Global Warming, a Global Energy Resource, and in the Environment section of this series, the OTC Improvement Thermodynamic Geoengineering can produce 31 terawatts a year for the next 3,000-odd years, and 25 terawatts in perpetuity thereafter. Energy costs. Visual Capitalist shows that the global primary energy consumption for 2023 was 620 exajoules, which equates to 19.9 terawatts. Oil was responsible for 32% of the energy consumed around the world, followed by coal at 26%, natural gas at 23%, and electricity production filled out the remaining 19%. The average price of oil for the year was $83 a barrel, and 1 exajoule is equivalent to 174 million barrels. The total cost of oil was about $3 trillion. The average cost for natural gas was $2.57 per million British thermal units, and 1 exajoule is the equivalent to 947.8 million BTU, so the total cost of the natural gas consumed in 2023 was $2.3 trillion. The average cost of coal per metric ton was $119, and since 1 exajoule is equal to 34.12 million metric tons of coal, the cost of the coal consumed in 2023 was $1 trillion. since 1 exajoule is the equivalent to 277.8 million kilowatt-hours, and the average global cost of electricity in 2023 was $0.1 per kilowatt-hour. The total cost of electricity was $2.77 trillion for a total cost of energy for the year of $9.4 trillion. The Ocean Thermal Energy Conversion Economics. Updates and Strategies of 2004 prepared for the International Energy Agency Ocean Energy Systems Technology Collaboration Program. Estimated archival ocean thermal energy conversion capital costs on the basis of the following equation. Plugging X in terms of net megawatt plant sizes, you get the Y, per the following table. To reach thermodynamic geoengineering's potential of 31 terawatts, 1,001 gigawatts plant would have to be built each year. The working life of these plants is estimated to be 31 years, so after the initial build-out you would have to replace the oldest 1,000 plants each year and replace them at a replacement cost of $5.6 trillion each year for approximately the next 2,938 years. The Ocean Thermal Energy Conversion Economics Update and Strategies considered a first-generation 50 megawatts closed-cycle plant ship using an 8% interest rate and an operating maintenance repair and replacement rate of 5.5% to come up with a total levelized cost of electricity with no profit, no environmental or tax credits of 37.8 cents per kilowatt-hours. And noted with less expensive heat exchangers, this could have been reduced to 25.6 cents per kilowatt-hour. Thermodynamic Geoengineering has a proprietary thin-film heat exchanger design with inline water flow and lateral flow of the working fluid that in an array forms a triangle that is both the most ridged structure and the one most capable of moving through water. It is comparable in cost to the plate frame heat exchangers examined in the Ocean Thermal Energy Conversion Study. This stern review on the economics of climate change argues that the costs of inaction on climate change are significantly greater than the costs of taking immediate action, largely due to its use of a low discount rate, which gives more weight to the potential future damages of global warming, essentially signifying a high interest placed on the issue of climate change and the need for urgent action to mitigate its effects. It argued that applying a promise to pay, or PTP rate of anything much more than zero to social policy choice on a problem like climate change is ethically inappropriate, but said a PTP rate of 0.1% would be acceptable. In the alternative, some argue that the most ethically acceptable discount rate ranges between 1 and 3% would ensure meaningful climate action without excessive economic burden today. Such a low discount rate would justify strong early action, recognizing that future costs for climate disasters and economic damage will far exceed present costs. Though others insist that moderate rates of between 3 and 5% balances investment in green technology with short-term economic needs. For the sake of this study, a conservative rate of 3% is considered. Whereas the economic update showed a 1 gigawatt plant would cost $5.6 billion, a more realistic cost is $2.6 billion per this table. And 1,000 of these plants at an annual cost of $2.6 trillion is 28% of the 2023 $9.4 trillion cost of energy, for 2/3 of the energy thermodynamic geoengineering would provide. In 2012, the cost of lithium batteries was $600 per kilowatt-hour. Elon Musk figured he could do better by buying the materials necessary to build batteries at the spot price of the London Metal Exchange, which he determined was 13% of the existing price. TG did something similar for its plants and came up with a price of $1.8 billion for a 1 gigawatt plant compared to the $2.6 billion shown here, but for comparison purposes the conservative latter value will suffice. When you add fossil fuel subsidies and the environmental cost of doing business burning fossil fuels, thermodynamic geoengineering derived energy is 16% of the existing cost.